this is where we ended up last time. We did a complete DC analysis. We came up with all the quiescent voltages. For transistor number 1, we marked the Q point. Transistor number 2, we marked the Q point. Again, this is the Q of the second one. Now, when it comes to the swing, that is variation, at the final output, there are variations. There is a variation in here. So we have to determine two types of peak-to-peak swing. What is available here from the driver stage? How much it can swing without getting in danger of cutting off or saturating the transistor stage. We will be able to determine easily how much swing the CC can give you without driving that transistor into saturation or the cutoff. So we've got to figure that out. In order to do that, it's actually very simple. You will look at the MPP available for each one of the stages. So MPP of stage 1, stage number 1. You will draw the dynamic load line, dynamic AC load line, all stage number 1. Slope. This is the AC load line that IC and the VCE will change in accordance with each other. I will just dash it in here, just draw some kind of a makeshift drawing to show you why. Look, if you refer to your model, this was GM1 times VBE of 1. This was your IC of 1. Partial drawing. This was the RC. This was the Z-in of 2, input of the second stage. So it was going to B of the 2. All of the input impedance of CC amplifier, input impedance, is absorbed into a Z-in 2, which we do have the value of that Z-in 2. The value of the Z-in 2, we figured, is equal to 17.5 kilo in that plane, looking in the direction of the base. Now, this is the collector of transistor 1. That's the emitter of transistor number 1. This is the VCE of 1. Signal change on the collector emitter of transistor number 1. See how IC and the VCE are related to each other. These changes, small changes, are related to each other via the model. You already have the model. If you took note, you have the model. This is just a partial drawing I want to show you. This is how you will account for it. You will say voltage from here to here is equal to minus IC1, which is the current that is collector changing, multiplied by RC parallel with Z in 2. So what is then IC1 over VCE1? It's equal to minus 1 over RC parallel R in 2. The collector current increment, collector emitter voltage increment, or small change, are related with these parameters. How does that reflect in this plane? Change VCE1, a change IC1. This change is going to be permanently constant. It's not going to change, that ratio. In other words, the ratio of the current to the voltage, speaking of slope of that red line, is going to remain constantly the same. Okay? So what will happen to the collector emitter voltage in here? The real voltage, overall voltage. The overall voltage will be the DC voltage, and this change is superimposed on that DC voltage. Therefore, the swing will be along this red line. One point will be here, which will cause the transistor to go to cut off because the collector current will shut down to zero in this rate if it goes forward, on that slope rate if it goes forward. And here, the transistor will reach, Vc equal to 0.7, will reach its saturation if the variation of the VCE becomes too big in this stage. I'm only talking in stage number 1, okay? So can we predict positive change in here? P swing is that one. The negative swing in here is going to be determined by this segment on the IC-VCE plane. This is the IC-VCE plane. The coordinates, you know, the IC and the VC, and then IB tracks, etc., etc. They are there. You know, there's an IB in here. No need to show that. IB quiescent there, and then your IB little is again changing, and it travels all the way along that line. So this is the condensation of everything together. So the P for this case will be always, for the stage number 1, your P will be equal to, it is the base of this right angle triangle. What you know, slope is -1 upon RC parallel RL, which already we figured how much that will be. This is the RC parallel to RL. No, that belongs to here, sorry. RC, no, I'm sorry, not RL. RC1 parallel to Z into, sorry, Z into, it's this one. RC1 parallel Z into, these two. RC1 parallel to Z into. So we need to figure out what is that quantity. -1 upon RC, that will be our tangent. Tangent means tangent of that angle, which is a negative. So knowing the height, which is IC quiescent, IC1 quiescent, knowing the height, knowing the tangent of that angle, we will be able to figure out what is P. Get used to the formula. It is IC quiescent 1 multiplied by RC1 parallel with Z in 2. So let's see how much is that part. It's equal to 17.5 kilo ohm. Here, kilo ohm multiplied by IC quiescent, that is 2 milliamp. Get 35 volt. Let me just check that again. This input impedance is no. I'm sorry. Z in 2 is 17.5. I have to take the 2 in parallel. So please let me correct them. So RC1 parallel with the Z in 2 is equal to 3K parallel with 17.5K. Okay, now it's correct. RC1 Z in 2 is equal to a little less than 3K. It should come out to that. So 3 invert and 17.5 invert equal, invert again, there it is. 2.56 kilo ohm. That's correct. Makes sense. Because I said it has to be a little less than 3, and it is. So what is then the P positive swing? Is 2 milliamp multiplied by 2.56 volt kilo equal to, so times 2, 5.1 volt. 5.1 volt peak. So this transistor that you see over here, the collector voltage can change, come down by 5.1 volt before causing the, it can go up before causing the transistor to cut off, completely cut off. P, this is the cutoff point. Cutoff for Q1. All right, next, negative swing. Negative swing is when the collector voltage is coming down. How much it can momentarily go down from its VCE quiescent value till, getting into the zone where it will be about getting saturated. So we need to predict N. N is negative swing is equal to VCE 1 quiescent less by 0.7. That's easy to compute. It's from here to here, this chunk over there. So N is equal to 5 minus of 0.7, and this is equal to 4.3 volt. 4.3 volt. Okay. Not bad. It's it can swing up to the limit of 5.1, can swing down to the limit of 4.3 when it is feeding the next stage. And what will be a symmetrical swing? The smallest of the two. We can see that. Smallest of the two is 5.3 volt. So we can say MPP1 is approximately equal to 2 times of 4.3 is equal to 8.6 volt peak to peak. So, excuse me. The preceding stage can deliver this much signal swing, 8.66 volt swing to the base. Okay? Now, let's check the condition for the second one. Because we said the voltage gain is nearly 1 for the second stage, then second stage should be able to deliver by the 1-to-1 ratio the same output in this point, 8.6 volt peak to peak. But we've got to check the condition for the second one. This plane that we plotted is not there for nothing. You see, this is going to enable us to predict how much MPP will this stage provide at the output. So the MPP in here goes along a different load line. Okay. I will draw a partial stage from the second one. So this is the MPP of 2, stage 2. So this is a similar drawing that I did in here, just partial drawing. It will be RE2 going into RL 220. This is 242 ohm. So RE2 parallel with RL will be equal to, we got it here, 115.20, 115.2 of an ohm. This is the current, and this is the IC, and this is the VCE, VCE of 2, number 2. That's the emitter of number 2. This is the collector of number 1, which is straight grounded because there is no signal over here. It's grounded, it's connected to the power supply. It's like being short, no change. Now, watching this stage, is there a relationship I can establish between IE, this is the IE, and VCE? Actually, we can do that. See here, if you take IC2 approximately equal to IE2, IC2 equal to IE2, is it valid? Yes, it is valid, because you see, the current in here is only 1% different from the current in the collector. It's like 1 plus beta over beta times the IC2. If we take that, we can say that VCE, if you write a Kirchhoff voltage loop around this is your voltage here, is equal to IC 1 multiplied by RE2 parallel with RL, and this is equal to minus of VCE2. VCE2. Why? Here, this current is going in, which is IC practically, was multiplying two resistors. But look at the relationship of the VCE2. Negative is marked here, positive is marked here. That's why this negative sign is posted there. It's again that famous violation of Kirchhoff Ohm's law, because I'm putting voltages backward. You see, this voltage is VCE minus here plus there. So this is your equation. Now, what is then, once more, IC1, IC2, I'm sorry, this is IC2. What is once more IC2 over VCE2? It's equal to minus 1 upon RE2 parallel with RL. In other words, from the output perspective, whether this was a collector, which we had it in this case, on the collector side, or it is sitting between emitter side, it's the same thing, practically. It's the same thing, same formula. So what is the increment now? Transfer it to here. You've got, again, proportional change. This is the AC load line for CC, AC load line for the CC. Slope, in this case, is minus 1 upon RE2 parallel with RL, with the RL. Now we have again the same thing about the swings. Okay, the swing, when the VC is increasing here, VC is increasing, it brings the transistor near to the cutoff point. So this chunk here, P, is equal to IC2 multiplied by RE2 parallel with RL. So we've got to figure it out. it is equal to, it's at 26 milliamp now. Multiplied by RE2 parallel to RL. It's a pretty small resistance. Remember, 240, 220, it's almost half of that, 110. But more accurately, 115.2. 115.2 ohm, which translates into I like to express this in kilo ohm, which will be 0.11, then times it by 26. So 0.1152 multiplied by 26, 2.99, like 3 volt. 3 volt peak. That's the positive swing available at the output. What is the negative swing? N, before it gets into saturation, is from the load line, and before striking the saturation is this chunk, which is 6.7 minus a 0.7. So N is equal to 6.7 minus a 0.7 volt. It's equal to 6.0 volt peak.
So 3 is smaller. Positive is smaller.
6.7, this one?
No, you said like, so positive, so the negative, positive side is the smaller side this time.
The positive side is, positive is smaller, 3 volt. 3 volt. Positive is 3 volt peak, negative part is 6 volt. So this is the P part. Now, from what we have over here, this is the situation here. The driver amplifier is doing great because it can give you a swing more than, see that? More than the swing the second stage can handle, okay? It can do that, has the potential to do that. Not necessarily it will do. If it did, it went to that limit, the second stage will mess up because it will go beyond its range. So your second stage, MPP for the second one, MPP2 will be approximately equal to 2 times of 3 equal to 6 volt peak to peak. Okay? Now, what will be the capability of what you have built here?
The smaller one.
Smaller one, obviously.
Yeah.
That one.
Mm-hmm.
In other words, what we have built in here, it can deliver 6 volt peak to peak across that 220 ohm resistor, without causing any of these transistors go into saturation or cutoff. Those are critical points to keep the circuit active. You know, you have ICs. ICs can deliver voltages, but what do you think the limit is? There is a limit with what you have designed. It depends on the type of your design, that it can handle that voltage swing range. A good IC, like a operation amplifier, when it is designed to operate with a power supply of plus minus 15 volt, the designer had in mind to design a swing that could be as close as possible to plus 15, as close as possible to negative 15. You'll never get there, first of all, with that supply size. The most is, good design, 15, like a volt and a half short of that. Maybe 13.5 volt positive peak. From the negative, maybe about the same amount. A couple of volt short of negative 15, minus 13. So it can give you about 26 volt peak to peak with a power supply of plus 15 minus 15, which has a gap of 30 volt peak to peak, but you can't go more than 26. Internal stages will saturate. That's the whole thing. You see, when we get to the differential amplifier, other type of amplifier, you will appreciate, you know, why we have got to watch the limits that it can operate actively. So the MPP overall, you can say overall maximum output will be MPP equal to about 6 volt peak to peak. 6 volt peak to peak. All right? Yes, sir.
How about, I'm still confused about when you do the slope.
one?
So I was wondering why instead so for RE2, I was wondering why the R.
Why these two are in parallel?
No, well, I'm wondering why we're not considering there's a,
Which
R pi. for-
No, because we are not concerned with it. We are concerned with this current and the voltage that is produced in here, which is nothing but minus VCE. This voltage from here to here is a minus VCE because that node is the same node as E. This node is the same node as there. So the voltage across these two parallel combination is literally the collector emitter voltage of that second
So we
transistor.
just worry about essentially the IC.
Yes, and we're writing this relationship, see? I, which is actually IE of 2, but we are approximating it, is equal to that current multiplied by minus VCE. If we want to be very, very accurate and write IC to that one, we can write, for example, instead of IE, this is IE, I can write instead 1 plus beta over beta IC is equal to times that is equal to VCE. So what will happen here, when you write on this slope, the only term that will add to it for accuracy, it will be a factor equal to 1 plus beta over beta multiplying that one. You see? So the bearing on that slope will be practically nothing because 1 plus beta over beta is 1. So this quantity here, to be accurate, it is 1 plus beta over beta. But that is approximately equal to 1. The slope of that line. Remember, this is an IC against the VC. It's not IE against the VCE. But we can make adjustment for that. This is IE multiplied by that, IE multiplying that, which is this voltage, because IE is going down, which is equal to minus VCE. But for IE, we will substitute 1 plus beta IC. Now I have a link between IC, VCE, which is this one, this quantity, slightly adjusted. The fact is, collector currents, the signal, is the same as the emitter current as the signal. The difference is 1%, it's that 1 over beta. So, we got the swing in here. It can deliver 6 volt peak to peak at the output, maximum 6 volt, out of a power supply that was 13 volt. DCC was equal to 13 volt. Okay, so where is this thing going to show up again? ECE 3200 lab. I think lab number 5, when you're making a cascade amplifier, made from a CE and a CC, and it is asking you design in such a way, so you've got to go find parameters, so that it can provide a designated value of MPP at the output. So you've got to watch for everything when you're designing it, right from scratch. And you will need this handout to guide you. how to figure it out. With a specified voltage gain, with a specified swing, that's it. Now, one more step I'm going to add to this problem is the following. How much power do you think will be available for this load resistor? Maximum power. So I can add to that. In here. Assuming the output can deliver 6 volt peak to peak to the 220 ohm load resistor, what will be the maximum output power? Power means average power. Sometimes they call it RMS power, which is the same thing. So how much power we can deliver to this 220 ohm resistor? Imagine an AC is occurring across that resistor. You know its value, it's 6 volt peak to peak. Okay? And you want to calculate how much power you will get to the resistor. Remember the law? V squared divided by R. But if it is AC, it is VO RMS squared over R, okay, RL. So the output power, P maximum, is VO RMS squared divided by RL. Now we need to calculate the RMS. The RMS is equal to peak to peak is 6. So what's the peak? Half of that, 3. Then what's the RMS of 3 volt peak? Is 3 over radical 2, all right? So you will write in here 3 volt peak over radical 2 squared divided by 220 ohm. So this will work out how many milliwatt we can capture at the output. That's equal to 3 times okay, or actually 3 square that here, square divided by 220. This is equal to 20 milliwatt. So P max is equal to 20.4 milliwatt. That's the amount of the power you can get to the load resistor. Now we know how much power we can get in here. I tell you what, 20 milliwatt sounds small power, right? But if this was an earphone, an earpiece, this one, the 10 milliwatt sound would be deafening. It would be that bad, so high. The threshold of human beings' power that you can detect sound is 10 to the minus 15 watt, like a picowatt. That's the threshold. 100 times of that is a comfortable sound level. In other words, a microwatt or 2 microwatt is just a comfortable level of sound. 10 microwatt is already too big. It's so sensitive. So if this is an earpiece, it will deliver a huge amount of power. 20 milliwatt is too much that we need. Okay. One more question, because I want to divert your attention to something else. How much power does the circuit consume? So I will erase it here and rephrase it in this form. How much power does the power supply deliver to the circuit? Known as PS. Okay, so you've got a 13-volt power supply in here. All those bias currents that you established in the circuit, it didn't come for free. It came from a source, right? Which source is that? It's this one. I of S. Actually, that I of S is not a constant because it is supplying a collector current here. It's supplying another collector current here. These collector currents are fluctuating, isn't that right? Because they go high and low. Here it is. Here's the proof, which is there, and so on. So your current that goes in here does have is coming from a fixed power supply, fixed voltage, with time varying current. Average power, if you look, it will be the product of the power supply voltage and the current it delivers. But because voltage is a constant, just in short, the power delivered by the power supply, P, supply is equal to VCC, this is constant, multiplied by IS average, or DC. The same quiescent things that you established in the circuit are those DC values. Remember we established here 26 milliamp and there 2 milliamp. It's not really 2, it goes up and down on the 2, but its mean stays there. So is on the other one, 26 fluctuates, right? But the mean, if you add them together, the mean is going to be the same because sinusoidal is symmetrical. So the mean current that is delivered over there will be IR of 1, IC of 1, IC of 2. So here, I of S is equal to IR of 1, current in the divider network. This is the DC current in the R1, R2 divider circuit, plus IC of 1, Q1 quiescent current, that is the mean current, plus IC2, Q2 quiescent current. So we need to put all of them together to figure out what is IS. This one is negligible, so small, because it has to be, it is 10 times of the IB. So this is IC, and therefore the current in here will be 10 times smaller than the current of IC. So this, we can claim too small. But you can calculate, no problem with it. Just take the voltage there, divide it by these two resistors, well, it will be down to nothing, basically, like 0.01 of a milliamp. Right? 10 micron. So too small, ignore it. IC1 will be equal to 2 milliamp. IC quiescent. IC2 is equal to 26 milliamp. Okay, so your total supply current, IS, is equal to 28 milliamp. Tad more than that because you ignored it there. Okay. So this is our current. What is the PS, supply power? Here is the answer. Therefore, PS is going to be 13 volt multiplied by 28 milliampere. It is equal to 13 times 28, 364 milliwatt. Okay. Total consumed power with this circuit that you have designed. It's going to consume 364 milliwatt, 0.36 milliwatt. It is energy per second delivered to the circuit. Where is it being dissipated? I'll tell you. It's dissipated here, here it has 2 milliamp in the collector resistance. VC times IC of that transistor. VC times IC of this transistor, power dissipation. IC times the RE, current, DC current in here, 26 milliamp with the 242. If you add all of those, you don't have to do that. Add all of those, you will come to this answer. So the smart guy, when you're analyzing an amplifier like that, it's called class A amplifier. It's famous as class A amplifier. Because class A amplifier means every individual transistor is conducting throughout the full cycle. It's called 360 degrees. Because it's sinusoidal. You see, if you take a sine here, going up and down, all the time, collector current is positive. There's no place that it will shut down. So the circuits that are of this type, that the IC is always positive throughout the full cycle, are called class A designs, or class A amplifier. So is this one, it's a class A amplifier, because its current is always positive. There are special amplifiers that only they will conduct in half of the cycle. What happens to the second half of the cycle? Is it truncated there? No. Another transistor will take effect to do the job. So you will need two complementary transistors, NPN, PNP, working together to build those kind of amplifiers. Those amplifiers, each transistor will conduct for half of the cycle. So from the 360, it's 180 degrees. From here, from 360, each transistor is 360 degrees full. So those that conduct for half of the cycle, known as class B amplifiers, they have a special feature, which is efficiency. In a minute, I will mention here what it is. I'll calculate for you. And those are much more efficient amplifiers when it comes to heavy power. But look, here, 364 milliwatt is not that much heavy power that you spend with your source. It's not that big. But instead, we are getting a good 20 milliwatt. This is a good output power from the circuit. Very simple circuit, very linear, and consumes, or it wastes pretty much, but it's not that much. Now, next question is, what is the power efficiency of this compound amplifier? Power efficiency. So I'll put it on the board. Power of the amplifier. It is denoted by eta, Greek letter eta. Eta is equal to PO maximum. This is the maximum output power available to the load resistor RL, okay, divided by PS, power supplied to the circuit. Overall power supplied to it. Let me write it overall. Overall power supply to the circuit, just to complete it, times 100%. Okay, so this is the classical formula. In other words, if you have an amplifier here, an input and a load RL, ground here, VCC, IS, okay? So PS is VCC IS, this product. In a minute we will calculate. Actually, we calculated already. This is the PS. How much you're giving to the circuit and how much power PO max it can deliver to your load resistor. Okay, that's known as power efficiency. So let's calculate our amplifier's power efficiency. This is the eta, is equal to output power maximum 20, where was it?
It's over there, 2024.
Where we calculated that? Oh, over there.
Yeah, yeah.
Oh, over here, I'm sorry, yeah. 20.4, here, 20.4 milliwatt divided by 364 milliwatt multiplied by 100%. This is the best amplifier can do, and it is pretty much disappointing. It's low, but we don't mind. I'll tell you again, 20.4 divided by 364. It's always less than 25%. That times 100, of course, 5.6%. No matter how good you design these amplifiers, how efficient you design them, it is always, the limit is 25%. And this is typical, way under the 25%. Now, generally for the amplifiers that we are talking so much about different configurations of it, they are all class A without exception. Their efficiency very poor, but we are not concerned with it because they are all low power devices. You're making a low power amplifier. You're not going to drive a 200 watt speaker, see, with this. You're not going to connect a 4 ohm resistance 200 watt speaker in here. To be worried, because if it's a 200 watt speaker in here, if the 5% is 200 watts, then you've got to deliver like 2 kilowatt to your circuit, which is not practical. But where is the application of this class of amplifier, this small signal, for small powers? Like a power in an earphone, or you are feeding a digital to analog to digital converter, they take very little power. Or Or radio communication. The input stage of the radios, receivers, satellite receivers, namely, cell phones, everything. They are receiving power levels in the order of nanowatt, even smaller than that. And they've got to amplify to only 1 or 2 milliwatt. That's it. 1 or 2 milliwatt, which these amplifiers can do. And they are linear, they've got wide dynamic range. They're completely adequate for radio frequency work, RF receivers, small signal RF, mixers, oscillators, name it, preamplifiers, radio frequency amplifiers, which you want to raise, for example, a picowatt, you want to raise it to 2 or 3 milliwatt. From pico going, so you need like million times of amplification. So it is good because their power gain is pretty high. They've got pretty high power gain. 2 CEs, you put them together, which is was the exam problem for you. And when you calculated the power gain should be in hundreds of thousands. The answer would be in the hundreds of thousands. Can't remember how much, but very high. Those are all class A amplifiers. So we got that efficiency. So we will say in all class A amplifiers, the power efficiency is less than 25%. At best, it is 25%. You don't get even there. 20% maybe. Okay, so this was the analysis for today. Let me check my time. Let's see, let's put that time, 20 minutes. Yeah, so remember that the topics that we did today, please attach it to the notes you took on Monday. It completes this class of types of analysis. Now I'm hoping to get to getting this thing started, which was giving me a hard time. I managed to get it started in the other room, but let me see if I can do it here. So we go here. All right. Oh, cap lock is on, I see. So disable that. Okay, cut me in. Now, let's go here, Siri is doing the same thing. It went through. So let me see if it will open. Let me see. It's one. Same thing. It's not opening my files. Same thing. It's not opening, I don't know why. 3200. Honestly, I don't know why it is not opening. Somebody messed up with his computer, altered the settings maybe. Not thinking that it affects others. That's the disk drive, you don't need the disk drive. This.
Professor,
Yeah.
I think someone can log on to Canvas and look at it that way, because you posted it on Canvas.
Oh, yeah.
Yeah.
Oh, somebody, well, this is mine, you know, it's my login, so it shouldn't affect me.
Well, you're not able to open the file, right?
Yeah,
Yeah, so we can view it online if we log in on Canvas.
oh, I see. Yeah, I see. Oh, on the campus, yes, I can do that. Of course, it is there, you know, whatever lecture is here, it is on Canvas. So you can follow it from there. Let me look at my, my topics. Yeah, I'll do it this way, and then you look up the details on the campus. I put all the files over there. You can open that from home. I want to go over common base amplifier and its performance characteristic. But I'm sure somebody messed up with the computer. You see, they took something out of it that it is not automatically opening. Otherwise, a minute ago I opened in the other class completely. So after class, I'm going to call that desk to come down and fix it for me. Okay, this topic, we covered common emitter amplifier, where emitter was grounded with a capacitor. We saw modified version of it, common collector amplifier, where collector was connected to the power supply. We called it common collector because there's no signal at the collector. Now, common base amplifier, what is that? So you will find handouts, notes, everything in a good shape on in the campus, known as CB amplifier. CB, common base amplifier. Again, it's a class A amplifier, just as usual. So it works as designed in this fashion. VCC, same old thing. R1, R2, same old way, same old principle. RE, RC. Okay? With one, let me write in here. The DC analysis is the same as CE amplifier, CE and CC amplifiers. Okay. But the way that the signal is injected into the circuit for amplification is different. So you've got a capacitor, CC1. The generator used to be here for input, no more. It straight goes to the ground. So input is completely, base is completely short-circuited to the ground via that capacitor. Next, signal is injected into the emitter and the base and the collector. This is the emitter, is injected to the base. V of I, maybe there could be a generator resistance here, V of the generator. Okay, and this is the V of I input, AC. And then the output is obtained from the collector, the same way. Plus minus, resistance here, R of L, and this is the output, VO. Pretty much it's the same circuit. It's used a little unusual way that the base is grounded. Signal is forced into the emitter with respect to the base. It's altered. So still you have that 0.7 volt from here to here, but it is changing in here due to the influence of the capacitor coupling the input signal. Now this current is called II. II, current, and the ratio of VI over II is called input impedance. Input impedance. And that is totally different from the input impedance of CE amplifier. Quite different. And that's of course the output. So collector change is coupled to the final load via a DC blocking capacitor or AC coupling capacitor. DC analysis, the same. Now, AC equivalent circuit. AC, small signal equivalent circuit. Okay, so how do we start with? We start with, VG, the generator, and its source, RG. This is the VI. It's going into the RE. RE. It's connected to the emitter. This is the emitter. Let me bring it down here. Into the emitter. Base is grounded. The one responsible is X of CC1 equal to 0. R pi is over there. You've got current source in here. This is your IC. Is equal to GM multiplied by the VBE. VBE is this voltage. VBE is that voltage across the R pi between base and emitter. And this is the voltage VI between this end, which is the actual input to the amplifier, and the ground. RC, this is VCE. VCE is connected to RC coupled to RL, and that is your output voltage, final output voltage, AC output voltage. So this is the equivalent circuit. The current is I of the I flowing in. Now we need to figure out the voltage transfer. What is VO over VI? We need to figure that out. So voltage gain, is VO over VI. We need to figure it out. That's your model you need to analyze. So we've got to link things together. Okay, so how do we go about it? First of all, this voltage is VI, which is between here. If you take a Kirchhoff voltage loop, go from here to here, and then from here to here, you're returning to zero. Isn't that right? That's the zero volt in this model. Plus minus, which is the VI. And then that node is the same as this node, which is the emitter here, base there, VB. So we can write by KVL, VI plus VBE is equal to 0. Therefore, VBE is equal to minus of VI. That's number one. Then relate IC into the VBE. IC is equal to GM times VBE, which is equal to GM multiplied by minus VI. We are substituting for VBE minus VI. Next. Here is your output voltage, VO. There is a current going in. This is the current. So that voltage, with respect to the direction of the current, you're violating the, remember, Ohm's law. So we can say VO is equal to minus IC multiplied by RC parallel with RL. Then we will substitute for IC the value in terms of GMVI. We will have VO is equal to minus of GM minus of VI multiplied by RC parallel RL. This will convert into plus, just to emphasize, there are two minuses. GM RC parallel with RL multiplied by VI. So we want to know what is the voltage gain, this ratio, VO over VI. The answer is VO over VI, known as AV. It's loaded because it includes RL, that's why it is loaded. If RL wasn't there, what? If you didn't have anything in here, it was just picking from that end of the capacitor, RL was infinity, it would be just RC, like before, only RC. So this voltage gain is now GM multiplied by RC parallel with RL. Significant thing about this equation is the gain is non-inverting because it's a plus. Gain is non-inverting. unlike the CE, unlike the CE amplifier. So the signal applied in here, time, this is the reference time 0, will come out of there much bigger, T, same reference time 0, the period T, and this is the period T. So the two sine waves will go together, as opposed to the previous one, which would go in opposite phase, because gain would be inverted in that case. Now, where do we use, oh, this is actually the one that is being used in communication. It has a much wider bandwidth. We will see soon when we do the frequency aspects of the transistors. Has a much greater bandwidth than CE amplifier. CC is good, it's wide bandwidth, but this amplifier also provides gain. That's the difference. CC had a gain of 1. It wasn't giving you anything in that term. Voltage gain was 1. But in here, you get the voltage gain you want. It's non-inverting, and it's going to be really wide band. We will look into it later. Now, one thing is remaining to figure out is what is Ri? We need to figure that one. Ri is Vi divided by I. So I have to figure it out. How much is that? Okay, so let's see. Here, we can relate that. II is equal to, this is the IC. Actually, this is the IE. IE, and IE is equal to, in a good way, in terms of IB, I can do that. I can, in terms of IC, 1 plus beta over beta times IC. I have IC over there. Okay, this current IE is equal to 1 plus beta over beta times IC. This is good old formula. Emitter currents are a little more than the collector. So we can claim that for the current in this path. Current in this path here, I of Re, I can say it is Vi over Re. Okay, the current right there. It's the Vi because that voltage is Vi over R. Therefore, current II is equal to 1 plus beta over beta multiplied by IC. IC is minus GM times Vi. This is the IC plus Vi over Re plus Vi over R. And here comes the answer. You have to factor this out and then derive Vi over II. If you did that, an easy formula would be Vi over Ri would be equal to RE going parallel with, 1/GM. So if you simplify, you will get that. And this will be your RI, the input impedance. So that translates into this one.